All right, welcome to this lecture on buffer solutions. So this is the third lecture from Chapter 11. And Chapter 11, the first two lectures focused on the calculations required for making solutions isotonic so that their osmotic forces are compatible with biologic fluids. This last chapter is completely different in the sense that we're not going to talk about isotonicity or osmotic forces, but keep in mind, these same formulations, such as eye drops, where we're trying to put a drug into an ophthalmic solution, we then need to add other items in there to make the final solution isotonic with the same osmotic forces as lacrimal fluid so we don't irritate the eye. Well, think about this. Most of these drugs are also weak acids or weak bases. And by dispersing them in water, regardless of what we use for the isotonicity adjuster, they can increase or lower the pH, and that could make the solution incompatible with the biologic fluids. Moreover, another big idea here is that the solutions, the drugs can in solution become either ionized or unionized. And that's important because only non-ionized drugs are going to be able to be lipophilic enough to be absorbed across biologic tissues. If it's ionized, it's hydrophilic, and therefore won't pass very well or be absorbed very well. So there's a lot of interplay about the effects of pH in our solution that will affect our drug and our drug's ability to be absorbed. So with that as a little bit of a background, some key things, and I will also preface this lecture. This is primarily to make sure you have the math skills for being able to use the formulas that are involved with pH and pKa and the dissolution constants and all of that. It goes beyond our capacity, to go through and review all of the chemical or all of the basic chemistry involved in acid-base solutions and so forth. But a little bit of background is important, or we don't even understand why we're doing these calculations. And let's start in the middle image on this slide. So on the right-hand side in the middle, we see kind of in the membrane, and we're looking at the ability of a drug, and this was maybe a good example of a drug like aspirin, where aspirin is kind of a weak acid. When you put a weak acid into the stomach, and that's shown there in the green with a pH of 4. So pH of 4 is a relatively low pH compared to neutral, which is 7. So you put your aspirin into the stomach contents, lower the pH to around 4, and the question is whether or not it dissociates, whether the parent molecule aspirin dissociates into its acidic form and gives up its hydrogen ion. Well, in the stomach, there's already so much acid, there is this kind of mass force to keep the hydrogen attached to the aspirin. So this weak acid isn't strong enough to actually dissociate. So it stays undissociated, which is good for its absorption. So that's why it can be absorbed across the membrane and into the blood, which you can see on the left-hand side where the pH is 7. So going back to the right-hand side in the stomach, so I'm saying that there's too much hydrogen ions to allow the aspirin to dissociate. So you can look that when you do the calculations here in this example, its percent ionization is 0.01%. Very little of it has ionized. So it has stayed as the parent molecule and been absorbed across the membrane and into the blood. So now looking on the left-hand side what the yellow figure says, what happens to aspirin as an example of a weak acid, when you raise the pH in this example, to 7, then that removes all of the pressure from the hydrogen ions, and there's so few hydrogen ions now that the acid can actually dissociate. So aspirin is willing to release its hydrogen ion when you have a much higher pH, something like 7. So since it loses that hydrogen ion, it becomes ionized. And here you can see when we calculate the percents on that, now we've increased our ionization up to 9% at a pH of 7. The take-home message for this, and the reason we're going to do these, is that we need to understand the relative concentrations of how much of our drug has become ionized, how much has not become ionized. We need to know the point at which that reaction is going to favor one side, meaning the ionization, versus the other side, meaning the non-ionized. And that's the figure on the left-hand side, and that's where we'll bring up and use this calculation for pKa, or Ka is the dissociation constant. We'll talk more about it. But the reason I'll just say in this little summary, pKa is a very important number. It's the value. When the pH is equal to the pKa for a drug, then the relative shift between ionized and unionized is equal. So when you get, depending on whether the drug is an acid or a base, when you shift pH either less than or sometimes more than the pKa value, you will shift the relative reaction to either more ionized or more unionized. So that's why the pKa is an important value, because depending on where the pH is in relation to pKa, you can predict how much drug will be ionized or non-ionized. The reason this, again, lastly, is a little more complicated is if you look on the far right, is what happens, that is, whether it becomes ionized or unionized, differs depending on whether the drug is a weak acid or a weak base. So to summarize, and this is where you can look on the figure on the far left as well. The figure on the far right gives you some examples of drugs and their pKa's, but essentially the summary is this. If a drug is an acidic drug, then at pHs less than its pKa, a majority of the acid will stay dissociated, so it will be absorbable since it's not become ionized. So low pHs below the pKa for acids allow it to be unionized and be absorbed. When the pH is raised above its pKa, then acids begin to dissociate. They begin to become ionized, and when they're ionized, then they can't be absorbed as well. The opposite is true for bases. If the drug is a weak base, then at low pHs, at acidic environments, the bases are already ionized. So as ionized, they're not going to be absorbed very well. It's not until the pH is raised above its pKa for a base that the molecules are then essentially forced back together and become unionized and therefore to be absorbable. So a weak base is going to be absorbed better at pHs above its pKa, whereas acids are going to be absorbed better at pHs below its pKa. So that inverse relationship is confusing, and all these terms I know can be confusing. But given that as a little bit of a background, I think we can now try to go ahead and just still focus on the calculations, focus on the numeric manipulations required when doing these kind of important calculations for being able to formulate solutions where we must take into account the pH of the final solution and what that effect is going to be on the drug's state about ionization or not. So our first question will be a brief review over pH and pOH. So let's put this discussion in context of a question. So the problem says, a pharmacist dissolves 150 milligrams of sodium hydroxide, which is the formula NaOH, that has a molecular weight of 40. So we're going to take the 150 milligrams of sodium hydroxide and dissolve it in enough water to make a 500 milliliter solution. What would you expect the pH to be, high or low? And to make that decision, obviously, we're going to need to actually be able to calculate the pH. And again, realize that 7 is generally considered a neutral pH, so any pH lower than 7 would be considered acidic. Any pH higher than 7 would be considered to be basic. So the question is, in this example, what is our final resulting pH, and we'll conclude whether that's acidic or basic. All right. So we got to do a little bit of chemistry. Let's look at what happens when we put sodium hydroxide into water. So the NaOH parent molecule will dissociate to some extent and free up both a sodium and a hydroxide. Okay, sodium being a positive and the hydroxide the anion. So sodium cation, hydroxide anion. All right. We chose sodium hydroxide because it is a strong base in this sense, and meaning that it almost completely dissociates. So we'll have basically have no parent molecule left, meaning the amount we start with entirely converts into either sodium or hydroxide. There will be no parent molecule, meaning sodium hydroxide, left after the reaction has occurred. Okay, now let's go ahead and define some things too. What is pH? pH is equal to the little value p stands for the negative log of some concentration. Since we're doing pH, it stands for the negative log base 10 of the hydrogen ion. Okay? Versus pOH, which would therefore stand for the negative log base 10 of the hydroxide ion. Okay? And again, these concentrations are going to be expressed in molar concentration, and that's important. The number we put in there has to be in the units of moles per liter, or capital M standing for molar. All right. So again, pH, negative log of the molar concentration of the hydrogen ion, or pOH being the negative log base 10 of the hydroxide ion in moles per liter. Okay, and lastly, you can kind of do the relationship. Basically, pH plus pOH is equal to 14. So you can rearrange that and say, therefore, that pH is equal to 14 minus the pOH. Okay, these are some basic chemistry definitions I'm kind of going through quickly and not explaining in a lot of detail, but that's the basic information we need to do our math. So let's make sure you can do our math, because we were given our amount of sodium hydroxide in milligrams. And we have to be able to calculate the pH, convert that eventually into the concentration of the hydrogen ion in moles per liter, so we can take the negative log base 10 of that. That's a long way to go, but we can do it one step at a time. Let's start with what we know. We were told we had 150 milligrams of sodium hydroxide, so I put that on top. Below that, I put the fact that we were told, concentration-wise, that weight of sodium hydroxide was going to be in a total volume of 500 milliliters. So hopefully you can see this. We have 150 milligrams of sodium hydroxide on top over the 500 milliliters. Okay? Now, let's ignore the volume for now, and let's first work on converting the weight of our sodium hydroxide into the number of moles or molecules. So the first thing I'm going to do is convert milligrams to grams. So I multiply it by 1 gram of sodium hydroxide over 1,000 milligrams of sodium hydroxide. That way milligrams cancel, and I'm now in grams of sodium hydroxide. I did that then so that I convert grams to moles by using the relationship on top of 1 mole of sodium hydroxide. We'll have 40 grams of sodium hydroxide, because 40 grams is its molecular weight. And remember, 1 mole of anything is equal to its molecular weight in grams. So now my grams of sodium hydroxide cancel, and I'm in moles of sodium hydroxide. Now, this is where it gets a little bit tricky. Remember, look at our chemical formula. What we said is that every 1 molecule of sodium hydroxide will dissociate and produce 1 mole of sodium and 1 mole of hydroxide. So my next step is to convert from the number of molecules of the parent molecule, sodium hydroxide, into just the number of hydroxide molecules. So I'm going to multiply that by the fact, but looking at my formula, I get 1 mole of hydroxide molecules for every 1 mole of sodium hydroxide. And that's because the formula is NaOH. There's 1 hydroxide molecule in every 1 sodium hydroxide molecule. So now the moles of sodium hydroxide cancel, and I'm in moles of hydroxide, which is what I need. Molar concentration is the number of moles, but it's the number of moles per liter. So while I have the correct units on top, meaning moles of hydroxide, I still need to convert my milliliters in the denominator into liters. So my last step is to multiply by the fact that there are 1,000 milliliters for every 1 liter. That way my milliliters units cancel, and if I do that math all the way across from left to right, my remaining units will be in moles from on top over liters. And the numeric value, by doing all that math going from left to right, is 0.0075 moles per liter, which is 0.0075 molar for the hydroxide concentration. Now that's important, okay? Because what I can now do is calculate the pOH. Since I have the molar concentration of the hydroxide, I can say that my pOH is equal to the negative log base 10 of the hydroxide concentration, molar concentration. So I set that equal to the negative log base 10 of 0.0075. So then if you use that and perform that calculation on your calculator carefully, that value should be 2.12. That's the pOH. That's important. Remember, we've solved all of this for under hydroxide. The next step would be to actually calculate the pH value, because remember, we know the relationship that pH is equal to 14 minus the pOH. So all we need to do is take the 14 and subtract our value for the pOH, which was 2.12. The difference between those then is 11.88. And that is the numeric value for our pH, 11.88. And as we said before, we can now conclude about the acidity or basicity of this solution by evaluating that number as it relates to 7. And since the value is greater than 7, we would conclude that this solution is a basic solution. Okay, now let's take a deep breath again. We've covered pH and pOH. That should be fairly straightforward. Now what's really important is to understand the term of pKa. Where does it come from and what does it mean? It is extremely important in pharmacy to be able to predict how much of a drug might be able to be absorbed based off of the pH of the solution it finds it in. So let's step back. And again, we have to take this different whether we're talking about a weak acid or a weak base. So this slide, we're going to talk about the dissociation of weak acids. All right. And by that, we would say call an acid abbreviated HA. Okay. An HA, a weak acid, you put in water and then it will dissociate and give up its hydrogen ion. Remember, it's an acid, so it is a hydrogen donor. We give an H plus, and then would have the resulting A, which would be considered the salt form of it. So it's what's left after the acid has given up its hydrogen. So it's the salt form. All right? So we have the acid HA on the left, basically producing a hydrogen ion and a resulting salt, which is the A minus. All right? The dissociation constant is called Ka. So Ka, the dissociation constant of a weak acid, is equal to essentially how much hydrogen ion and salt are formed concentration-wise compared to the concentration of your initial acid. Would you agree? The higher the numerator is, that is, the more the reaction goes to the right and forms the hydrogen and salt form, then the greater the reaction, the less concentration of your initial acid that you should have. Conversely, if the reaction doesn't go very far, if it doesn't dissociate, then again, you would not have a very high concentration of hydrogen and salt on the right compared to your initial. So Ka is just a way to compare the concentrations of the reaction over the concentration of the initial product, in this case, the acid. All right, so that's Ka. Well, what is pKa? pKa is just the negative log of the Ka value. All right. So why would we ever express as pKa versus Ka? Because when we actually do the math, the Ka values tend to be very small numbers and 10 to the minus whatever. So it's easier numerically to just express them as their negative logarithms or their p values, just like it is for pH or pOH. Okay. So in the end, for a weak acid, let's talk about the Henderson-Hasselbalch formula. This is the important formula I know you've already had in chemistry many times, and I don't want to go through the whole derivation, but the formula we're going to use and be able to apply here in some pharmacy examples is this: that for a weak acid, the pH of the solution is equal to the pKa of that drug plus the log of the concentration of the salt divided by the concentration of the acid. And this is that molar ratio. We're going to do some calculations here in a minute. That's really important. It's the relationship. Remember, we said the salt is the thing that is formed once the acid gives up its hydrogen ion. So the salt is on the right-hand side of the equation, whereas the acid was our initial product that we began with that still has the hydrogen. Basically, it's the hydrogen donor, if you will. So it's the relationship of the amount, concentration, and this is still in molar concentration. So the concentration of your product, the salt on top, divided by the concentration of the acid, the thing you started with. All right? And that's the value, and that's the equation we'll use for weak acids. Unfortunately, it's not exactly the same when we're talking about a weak base, because the formula for a weak base is similar, but I say similar but different. So in this case, when we have a drug that's a weak base, we start with the parent molecule on the left-hand side, and on the right-hand side, essentially you have the base gives up a hydroxyl. Instead of giving up a hydrogen ion, it gives up a hydroxyl molecule, which is negative. Therefore, the resulting salt in this case is positive because instead of giving up a hydrogen, it gave up a hydroxide, which is negative. So again, the salt is positive relative to the hydroxide it gave, which is negative. Okay, but in the end, you still started with a base to begin with. So the BOH would be considered the base. The B plus is considered the salt because it's the resulting form that resulted when the base gave up a hydroxyl, which is negative. Okay, now we can, since it's a base, it's not called a Ka, it's a Kb. The dissociation constant for a weak base is Kb. It's calculated the same way. It's the concentration of the resulting products, meaning the salt and the hydroxide molecule, over the concentration of the initial base that you started with. Okay, so it's set up the same, but we call this Kb since it's the dissociation of a weak base. And we do the same thing. A pKb is going to be equal to the negative log base 10 of the Kb concentration. And again, we do that again so that the values are larger. All right. So in the end, we care about this because we're still trying to get to our Henderson-Hasselbalch form of an equation, but now for a weak base. And so I've showed a little bit of the derivation here, but for the sake of both of our sanities, and I don't think the derivation is important as just being able to correctly use the formula here. So for a weak base, the Henderson-Hasselbalch formula you would use would be that the pH, again, pH is now equal to, and this is why it's different because it's a base, not an acid, but the pH is equal to 14 minus the pKb plus the log, and this is important now, of the base over the salt. Okay, so these concentrations are a little bit different than they were before for an acid. So now the molar ratio for a base here is going to be the base, that is the concentration in moles per liter of the initial base that we started with on the left-hand side of the formula, over the concentration of the resulting salt, which would be the B plus in this example. Okay, so the initial base divided by the concentration of the salt formed when the reaction occurs. And that's the Henderson-Hasselbalch formula that we would use for these calculations for a weak base. All right, that's enough background and derivation of these formulas. Let's go ahead and put them to use. And so the first question we're going to use these equations to solve for is for molar ratio. So the question is, what is the molar ratio of sodium acetate to acetic acid? Okay, so stop there for a second. In this case, the ratio of acetic acid, in this case, would be the salt, because it would be considered the hydrogen ion acceptor, versus acetic acid, which is considered the acid since it's going to be what donates the hydrogen ion. Okay, so we want the molar ratio of the salt to the acid that would be required to prepare a buffer solution with a pH of 4.5. The only additional information we would need to solve this would be that the pKa value for the acid, which is acetic acid in this example, is 4.05 at 25 degrees Celsius. All right, stay calm. Remember, we always on these questions tend to fall back on our Henderson-Hasselbalch formula. So that said, that formula says that the pH is equal to the pKa plus the log of the relative concentrations, the molar ratio of salt over acid. And in this case, we said the salt was sodium acetate and the acid was the acetic acid. So it would be those concentrations in moles per liter, molar concentrations. Well, that's what we're trying to solve for. Remember, the question wants to know what the molar ratio is. So really, we can fill in every other variable in that formula. So let's rewrite that as, in this case, since we know the pH we want is 4.5, we would say that 4.5 is equal to the pKa we were given at 4.05 plus the log of our concentration of salt over acid. Well, let's simplify that again by subtracting 4.05 from both sides. Now we know that 0.45 is equal to the log of the salt over acid concentration. The only trick mathematically for some of you at this point is knowing how to cancel a log. We cancel the log on the right-hand side by taking 10 to the x on both sides. We raise both sides of the equation by the power of 10. So on the left-hand side, we would have 10 to the 0.45 power equal to 10 to the log of the concentration of salt over acid. And so, again, we would just use on our calculator 10 raised to the 0.45 power equals 2.82. Got that from our calculator. Set that equal to, remember, raising the log base 10 of something by 10 cancels each other out. So the 10 to the log cancels out both of those, so we end up with just the concentration, the molar ratio of salt to acid, and that would be our final answer. So in this question, the molar ratio is 2.82, and that's the ratio of salt to the acid. All right, let's do some other buffer calculations using these, again, this molar ratio idea. We'll take this, what we just solved, and go a little bit further and show you how you could actually use it to calculate the amounts of ingredients you would need to prepare a buffer solution. So, continuing from the last question, the question says, the molar ratio of sodium acetate, salt, to the acetic acid, which was the acid, is 2.82. We just calculated that. Now we're saying is that the total buffer concentration is going to be 0.02 molar. All right? What we're wanting to solve for is how many grams of the sodium acetate with a molecular weight of 82 and how many grams of acetic acid with its molecular weight of 60 would need to be used. So the weight of both of those in grams need to prepare 1 liter of this buffer solution. All right? So where do we go for this? This, I think, is kind of a complicated question here because we need to use the molar ratio to determine the moles we need for both the acid and the base. Or the salt, I should say, not the base, but the salt. So let's start on the far left here on the top, and we'll kind of walk you through this. Remember, what we solved in the previous question was the molar ratio, and said that was 2.82. But what did that equal? That equaled the molar concentration of the salt, or the sodium acetate, over the molar concentration of the acid, or the acetic acid. Well, let's solve for one in terms of the other. We can't have both of those. So we could rearrange that to say that the salt concentration then by itself is equal to 2.82 times the acid concentration. Okay? That'll be important here, and you'll see why. The next step is we were told that the total buffer concentration was 0.02 molar. So in your mind, you need to understand total buffer concentration. Well, the total concentration is just the sum of the two things in the buffer. It's either acid or salt. So if you add the acid to the salt, that's how you get the total. And we said that the total was 0.02 molar. So now the problem is we need to rewrite that formula, that is acid plus salt equals 0.02, and we can't have two variables in it. We need to have just one variable. But we just said above there that we could re-express the salt concentration as 2.82 times the acid concentration. So let's substitute that into that formula, and doing so would give us the formula that says the acid concentration plus 2.82 times the acid concentration is equal to the 0.02 molar. So if we add that together, acid plus 2.82 acid gives you 3.82 acid. So we now have 3.82 times the acid concentration, still equal to 0.02 molars. Now divide both sides by 3.82, and you find that the acid concentration by itself is equal to 0.02 divided by 3.82, which numerically results in 0.00524 molar. Phew. We have determined the concentration of acid we will need. That's pretty cool. What we still got to do is go back and now figure out our salt concentration. And that's easy breezy because we said that the acid plus the salt equals 0.02 molar. Now we know the acid concentration is 0.00524 molar plus the salt concentration equals 0.02. Just solve for salt by subtracting, and you get that the salt concentration is equal to 0.01476 molar. Okay? We now know the molar concentration of both the salt and the acid. That's great. What does molar mean again? It means moles per liter. Okay? So to solve this final question, which actually wanted to know how many grams of both the salt and the acid are needed to prepare 1 liter of buffer, all we need to do, and I'll just, again, you can see the formulas here. If I just start for the acid or the acetic acid, remember we said its required concentration is 0.00524 molar. That's the same as 0.00524 moles over 1 liter. Okay? So we already have the amount of moles we need per liter. The only thing we got to do is convert that to grams. So let's multiply that by the formula weight in grams, which we said for acetic acid is 60. So 60 grams on top for every 1 mole. So I'll remind you, a mole is defined as the molecular weight of a substance in grams. So now moles cancel, and we will be in grams per liter, which is what we want to solve. So if we take 0.00524 times 60, the final numeric answer would be 0.314, and the units are grams per liter. So we have solved the weight of grams of acetic acid we need to make a liter of this buffer. Last step is to find the same thing for the salt, or the sodium acetate. We said its concentration was 0.01476 molar, which is 0.01476 moles over every 1 liter. Let's multiply it by its formula weight, which was given to us as 82 grams for every 1 mole. That way the units of moles cancel, and if we multiply that across, your final answer would be 1.21 grams per liter. So this kind of shows you the culmination of how these formulas can be actually very useful for being able to calculate the requirements, the weight we need for various parts of our buffer solution based off of what we're trying to accomplish, what sort of pKa we have for our acid, and the total concentrations, and how they relate to each other. All right. Now that you're an expert with using the basic Henderson-Hasselbalch formula, let's kind of blow your mind here a little bit, because we can. What could we do to change? Remember, it really is just for acids. We'll start with this idea of an acid. What happens if you add a strong base to that solution? So before you add the base, you use your Henderson-Hasselbalch. You can see the pKa of something shows you the relative concentrations of the acid and the resulting salt in relation to the amount of acid you start with. All right, so we have all of those in equilibrium. What happens then when you add a strong base? What does it change? The base will essentially react with the acid. Okay, so what happens in the slide, we're going to call that new acid. The new acid concentration is the acid concentration that results after the addition of the base. And what it's equal to is the original acid concentration minus the concentration of the base, because the base chewed up or used up the amount of acid. It reacted together. So you have less acid after the reaction because the base used it up. So the new acid is going to be less than the original acid by the concentration of the base added. So you're losing acid. Well, if you lose acid, what do you gain? You gain salt. So what happens is the salt concentration, that is essentially the hydrogen acceptor in the formula, essentially increases by the concentration of the base added. So if the acid is reduced by the concentration of the base, then the salt increases by the concentration of the base. Therefore, when all that's said and done, you still would determine the resulting pH of that solution after the addition of the base by the same formula. In this case, the pH is equal to the pKa plus the log of. But keep in mind, now you would use the new salt concentration divided by the new acid concentration. So it's still salt over acid, but you would use the new concentrations that result after the addition of the base. Okay? Well, let's put that into an example. Let's use that information and do a sample question. So this question, and it's about the change in the buffer pH to an acid solution when you add a strong base. All right, so the question is, what is the change in pH on adding 0.02 moles of sodium hydroxide to a liter of buffer solution containing 0.05 molar sodium acetate and 0.5 molar acetic acid? The pKa of the acetic acid solution is 4.76 at 25 degrees Celsius. Okay? All right, so where do we start with all of that? Well, what we need to know is, to know the change in the pH, we have to know what the pH was to begin with. Since we've already done that already, and before we make any changes based off of any sort of addition of the sodium hydroxide, let's just calculate the pH of the solution before adding the sodium hydroxide. Okay, the initial pH. And we do that using the Henderson-Hasselbalch, saying that the pH is equal to the pKa plus the log of the salt over the acid concentration, again, in molar concentration. Good news, we have all that information already. All we got to do then is say that pH is equal to the 4.76 plus the log base 10 of the 0.5 molar of the salt, that is the over the 0.5 molar of the acid. So remember, the sodium acetate is our salt, so the 0.5 molar for that on top. But we have 0.5 molar of the acetic acid, which is the acid that we put on the bottom. So essentially, we are taking the log of 1. 0.5 divided by 0.5 is 1. So essentially, the log of 1, log base 10 of 1, is 0. Therefore, the pH is equal to 4.76 plus 0. Therefore, our starting pH of this solution before we add any sodium hydroxide is 4.76. Okay? Now, the next step is to figure out what happens to the concentration of our salt and our acid after we add the base. Okay, well, we're going to calculate and call that again the new acid concentration and the new salt concentration. And we said that the new acid concentration is going to be equal to the original acid concentration minus the concentration of the base added. And the only thing I'll warn you about for all of this stuff is our units have to be the same. So we should express everything in molar concentration, so our units are the same. We already have that. That's nice. We know our initial concentration of the acetic acid was 0.5 molar, and we're adding 0.02 moles per liter. So 0.02 moles per liter is the same as 0.02 molar, or capital M. So we can just subtract 0.02 molar as the concentration of the base added. When you do that, you can see that 0.5 minus 0.02 is equal to 0.48 molar. So that's the new concentration of the acetic acid in our solution after we've added the base. Let's do the same thing for the salt. Our new salt concentration is going to equal to our original salt concentration, which we said was 0.5 molar. Now, though, we're going to add to it. Remember, we generate more salt as the acid uses up the base, or the base uses up the acid. So our salt is going to go up by the concentration of our base, which we said was 0.02 molar. You add those two together, and we see that our new salt concentration is going to be 0.52 molar. Now that we have those two new or revised concentrations, we can go back to our same old Henderson-Hasselbalch formula, and let me just go ahead and put those numbers in. So pH is equal to the pKa, which we said was 4.76, plus the log of the concentration of the salt, which we said is now 0.52 molar, divided by the concentration of the acid, which is now 0.48. All right, so if you take 0.52 divided by 0.48 and take the log base 10 of that value, you see that that number is 0.03. So in the end, the pH is going to be the 4.76 plus that change, which is 0.03. Therefore, our resulting pH is going to be 4.79. Keep in mind, we're almost done. That's the pH after we've added the base. The question asked, what is the change in pH? So our last step is to take where we ended up at, which was the 4.79, and subtract where we started from, which was the 4.76, and see that we had a 0.03 increase in pH as the result of adding the 0.02 moles of sodium hydroxide into this liter of buffer solution. So your final answer in this case would be 0.03 increase in pH. All right, well, let's put those formulas into action by looking at what happens when we take a base in solution, in a buffer solution, and add a strong acid. Okay, so the question reads, what is the change in pH on adding 0.1 mole of hydrochloric acid, that's our strong acid, to a liter of buffer solution that contains 0.05 molar of ammonia, which represents our base, and 0.05 molar of ammonium chloride, which would be our salt? The additional information they give us is that the Kb value, now it's not the pKb, be careful, it's just the Kb value of ammonia, the base, is 1.8 times 10 to the negative 5. Okay? That's a lot of information again. Where do we start? Well, the same place we started before, because in the end, we're wanting to know the change in pH. And to know the change in pH, you have to know the initial pH. So let's solve for the initial pH. We'll do it the same way, but since this is now a basic solution, we have to use the correct formula that says that the pH is equal to 14 minus the pKb, so we're going to have to determine the pKb, and plus add to that the log of the concentration of now the base divided by the salt. All right? Well, let's put some numbers into that. So the pH would be equal then to 14 minus, now this is the only trick, remember that a little p stands for the negative log base 10 of something, so pKb would be the negative log base 10 of the concentration that we were given of 1.8 times 10 to the negative 5. Okay. To that, then we're going to add the log base 10 of the concentration of the salt, or I'm sorry, the base, which we said was the ammonia at 0.05 molar, divided by the concentration of the salt, which was the ammonium chloride, which was the 0.05 molar. So again, the 0.05 divided by 0.05 is 1. The log base 10 of 1 is 0. So as you see, we go down a level, then we know that the pH is equal to 14 minus the 4.74, which is essentially the pKb, plus 0. Therefore, the pH is equal to 9.26. That is our initial pH. Next step would be to calculate the concentrations of both our base and our salt after it reacts with all of the hydrochloric acid that we add to it. We said that the base concentration is what's going to react with the acid and be used up. So we would take our original base concentration of 0.05. Let's subtract from that the concentration of the acid we are adding. And we said to add 0.01 mole per liter of buffer. Well, that's 0.01 moles per liter is 0.01 molar, so the same concentration as our base concentration. So we subtract 0.01 molar, and we would see the resulting base concentration would be 0.04 molar. Salt, same thing, except for it's the salt that gets formed. As the acid reacts with the base, we form more salt. So let's take our initial salt concentration at 0.05 molar, add to it the concentration of the hydrochloric acid, which was 0.01 molar. You add those two together and see that our final increased salt concentration is 0.06 molar. Now all we have to do is go find the pH of this resulting solution by using that same formula as before. So fortunately now, remember, we still have the same pKb, so we can just say that our pH is equal to 14 minus the 4.74 plus the log base 10 of the concentrations of 0.04 divided by 0.06. So if you take that number, 0.04, divide that by 0.06, get that number, take the log base 10 of that value, you would get 0.18. So in the end, to determine for the final pH, we would take the pH of 14 minus the 4.74 minus the 0.18 and see that our new pH after the addition of the hydrochloric acid is going to be 9.08. So like before, to find the final answer, which is the change in pH, we would take what we ended up with, which was the 9.08, and subtract from it where we started, which was the 9.26. So 9.08 minus 9.26 gives us a negative 0.18, showing that we have a decrease in pH. That is, pH became more acidic by a 0.18 pH value. Okay, and that's the answer to this question. All right, we're to our last question for this lecture. I love this one. This is a good one because it brings together both the issues of isotonicity and the use of buffer solutions in, for example, the formulation of an ophthalmic solution. So what keeps in mind is that in the practical application when we're doing these in a compounding pharmacy is we oftentimes want to use pre-formulated products that makes life easier. So for example, many times ophthalmic solutions are compounded using what we call Sorensen's phosphate buffer. It's a commonly used available buffer solution, and it uses two different things. It combines dibasic sodium phosphate with the formula Na2HPO4 with monobasic sodium phosphate with just Na but H2PO4. Okay, so within there we have both kind of a relative acid and a relative base combined together in this phosphate solution. So, and it comes pre-formulated. We don't have to weigh those out, but we have to measure the correct volumes of those two components, as you'll see here in a little bit. So between the essentially the salt form and the dibasic sodium phosphate and the acid form, which is the monobasic sodium phosphate, we can mix these solutions in the right amount to create a buffered solution at whatever target pH we may want. And you'll see that here in a minute. Because the problem that we're going to have, so the question we're trying to ask is to calculate the amounts of ampicillin with an E value of 0.16 and both of these phosphate solutions and any additional sodium chloride needed to prepare the following prescription. Okay, so the prescription calls for ampicillin sodium at a concentration of 30 milligrams per milliliter. Then it says to add enough of the Sorensen's phosphate vehicle and additional sodium chloride such that you get a final total volume of 15 milliliters and that this solution in the end is both sterile and buffered and isotonic at a pH of 6.6. And that is exactly why all of these content has been grouped together into this one lecture, or this whole topic over Chapter 11, is that, for example, for isotonic or for IV solutions or ophthalmic solutions, we often need to make them not only sterile, but buffered and isotonic. So that's what we're trying to do here in this prescription. So where do you start? There's a lot of stuff going on here. Well, let's start by looking maybe about the isotonicity issue. And one of the ways that we learn to calculate isotonicity is by using the sodium chloride equivalent method, since we know how much sodium chloride it takes to make a solution isotonic, meaning that 0.9%. So the first thing, since we know how much ampicillin is going to have to be used in our product because of the required concentration, let's calculate how much sodium chloride that amount of ampicillin would be equivalent to. Okay, so to do that, let's start by taking the volume we're going to compound, which is 15 milliliters, and multiply that by the concentration of ampicillin, expressed as 30 milligrams per milliliter, so that the units of milliliters cancel. And let's go ahead and convert that to grams. So we'll go ahead and multiply that by the fact that there's 1 gram over 1,000 milligrams. Milligrams cancel, and our final units would be grams. So if you take 15 times 30 divided by 1,000, you would get 0.45, and it would be grams of ampicillin. Okay? Now, this is an important reminder. How do we convert from the weight of ampicillin to the weight of an equivalent amount of sodium chloride? Well, that's where the E value comes in. So we would take our 0.45 grams of ampicillin times the E value expressed as 0.16 grams of sodium chloride. So remember, the number goes with the grams of sodium chloride over every 1 gram of ampicillin. Now, grams of ampicillin cancel, and we multiply across. Our value will be in grams of sodium chloride. And 0.45 times 0.16 gives us a numeric value of 0.072 grams of sodium chloride. So what that means is what we know. By using the amount of ampicillin we need to make 15 milliliters have 30 milligrams per mil, which was our 0.45 grams of ampicillin total, we know that ampicillin is equivalent to osmotically 0.072 grams of sodium chloride. Okay, so we're going to have to use that number again here in a little bit, but we're not quite ready to mess with it again, so just keep that number in mind. Okay, now we can take into consideration the relative volumes of the commercial solutions we're using for our Sorensen's phosphate vehicle. As a reminder, it's really nice to be able to use this pre-prepared solutions, and they come in the same concentration. So we have one solution concentration of 0.0667 molar of the monobasic sodium phosphate. And over here we have the other pre-made solution that's 0.0667 molar of the dibasic sodium phosphate. So they come in the same concentration of the two different solutions, monobasic in one solution, dibasic in the other solution. Now, the manufacturer provides this table that says, well, depending on whatever pH you want, use these various volumes of the two different solutions in this combination to get this final pH. So if we use this table and go over to the third column, and keep in mind that what we're wanting to compound is an ophthalmic solution that has a final pH of 6.6. So in the third column, let's go down till we see the pH value of 6.6. Then go to the left of that value, and it shows us to get a volume, or a pH rather, of 6.6, you need to use 60 milliliters of the monobasic sodium phosphate in combination with the 40 milliliters of the dibasic sodium phosphate. You mix those two volumes of solutions together, and you get a resulting volume of 100, right? 60 plus 40 is 100. So you mix those two together, you would get a total volume of 100 milliliters, and the resulting pH would be 6.6. Okay? Now, we'll leave off the sodium chloride far right column for now. We'll come back to that. But right now, let's just focus on determining the relative volumes of the monobasic and the dibasic sodium phosphate we need to make our ophthalmic solution to be 6.6 pH. All right? Well, you think, well, we already know that. The only problem is we're not making 100 milliliters of our ophthalmic solution. So we're going to have to readjust the volumes to account for our smaller total volume. That's easy to do. Let's start with the monobasic sodium phosphate. The table tells us to use 60 milliliters of that solution. We know that 60 milliliters then will be mixed and dissolved or dispersed up to 100 milliliters of total solution. So 60 milliliters is the monobasic out of 100 milliliters of total solution. Let's set that equal to some value x over 15, because we know 15 milliliters is the total volume of the ophthalmic solution we want to compound. Therefore, x is going to be equal to the volume of just the monobasic sodium phosphate we would need to use. So if we solve for x, we would take 60 times 15, divide that by 100, and we see that x is equal to 9 milliliters. That means 9 milliliters out of our 15 needs to be the monobasic sodium phosphate. Well, let's do the same sort of proportion calculation for the dibasic sodium phosphate. Remember, the table told us to use 40 milliliters of that solution, and that 40 milliliters would be in a total volume of 100 milliliters. We set that equal to some unknown x over 15. Since 15 is the total volume we're trying to compound, let's solve for x. So 40 times 15 divided by 100, and x would equal 6. And the 6 milliliters represents the volume of the dibasic sodium phosphate to use. And it should make sense that if we take the volume of the monobasic of 9 milliliters plus the 6 milliliters from the dibasic, that it would be a total of 15 milliliters. And that's what we're trying to compound. So we now know the relative volumes of our two different solutions to use, so that when we mix them together, that is 9 milliliters of one plus 6 milliliters of the other, we get a total of 15 milliliters of solution, and it will be at the right pH of 6.6. Fantastic. We're almost done, right? We know the volumes of our two different solutions to use. We got the right pH. The only thing we haven't completed yet was our calculations for isotonicity. So let's do that. So let's go back to this table, and I've kind of shrunk it up to where we're only looking now at the values for this pH of 6.6. We need to look at the value on the right-hand side, and it says the amount of sodium chloride required for isotonicity in grams per 100 milliliter. Or essentially, at this pH of 6.6, you need an additional on top of the isotonicity being contributed by the two different phosphate buffer solutions, which you still need to add is 0.49 grams of sodium chloride per 100 milliliters. So it's trying to tell you the additional sodium chloride to add so that the final solution is isotonic. All right? That's awesome. It's really good, but the only issue here is we need to adjust that number again because we're not compounding 100 milliliters. So let's take the amount of sodium chloride they say we still need, the 0.49 grams, over the total volume that recipe is calling for, which is 100 milliliters, and set that equal to some value x over the 15 milliliters, which is the total volume that we are compounding. If we solve for x, we would take 0.49 times 15, divide that by 100. X would then equal 0.0735 grams. That's grams of sodium chloride. That's the total weight of sodium chloride we would need. You take that sodium chloride, add it to the two phosphate buffer volumes, and that solution isotonic. So our target total is 0.0735 grams of sodium chloride. So let's take that. From that, we need to subtract the amount of sodium chloride equivalent we're getting from our ampicillin. So if you remember way back, that was kind of the first question we answered, was that based off our concentration of ampicillin, the equivalent amount of sodium chloride the ampicillin will provide is the 0.072. So if we subtract that, numerically our final answer is 0.0015 grams of sodium chloride. So that's the additional sodium chloride we would need to add to make the combined with the ampicillin and combined with the sodium phosphate buffer solution will make a total of a isotonic solution. And really, we're done. So let's just summarize our compounding procedure. What we're going to do is we're going to weigh out the 0.45 grams of ampicillin. All right, because that's the weight of ampicillin to get the right concentration in our eye drop. Okay, now to that, we're then also going to add 0.0015 grams of sodium chloride. That's then the value we just calculated. We take those two solids and we dissolve them in 9 milliliters of the monobasic sodium phosphate and 6 milliliters of the dibasic sodium phosphate. We mix that all together. It will dissolve. We've got our two solutions mixed. We've got our two solids dissolved in there. So it has the right weight of ampicillin to give us the right concentration, and the additional sodium chloride on top of the osmotic forces produced by the sodium phosphate buffer will make the final product isotonic. The last thing it needs to be is sterile. So what you would then do is take that solution into a hood, into an aseptic environment. You would then filter it you'd sterilize it through filtration. You basically pass this solution through a really, really fine filter that would filter out any of the bacteria that might be in there, and then you package it into a sterile container, and you're done. And that would be your final product. So hopefully you found this kind of review helpful, and I really like this last question tying it all together. That is, you need to use your knowledge of isotonicity along with your knowledge of buffer solutions to make a good final product.